So homework 4 has been posted. Um, and I've added new notes to go along with that, which will be covered probably sometime next week. So I think I might be able to finish all the material like this week and next. Especially since I don't seem to have much in the way of notes. Um, Although I think I might be adding something to it. Um, just to make sure that I cover all the important things. All right. So, um, so last time I started time-dependent methods for time-dependent PDEs. The basics of time-stepping methods and uh, showing that the simplest time-stepping method of all, forward Euler or explicit Euler, actually converges. But such a simple time-stepping method, like Euler, is only a first-order accurate. So goal today is to give some examples of methods that are higher order accurate. So with a whole family of methods that are meant to be relatively simple to implement and also deliver higher order accuracy. And you likely heard of these methods at one time or another. Runge-Kutta. Okay. Right. Um, so, to recap, let's get Euler for the ODE, or system of ODEs, y prime equals f of t y is given by y plus 1 equals yn plus delta t f tn yn. It just occurred to me, I can't remember if last time, it's common practice to identify a computed solution using the time step index, n, as either a subscript or a superscript. And I can't recall if I used it as a subscript or superscript last time. Good, because that's what I have in today's notes. So at least it's consistent, because a lot of times I use a subscript, but okay, so no problem there. So, all right, okay, so this is explicit Euler, and the error is of order delta t. So first order accuracy is delta t to the first power. Okay. So, and the thing is, you think of this right-hand side as first two terms of the Taylor expansion of yn plus 1. Around the center, which is Tn. So that gives you the idea of why it's first order accurate, because we're using terms from Taylor expansion. Also, why it's only first order accurate, because we stop after two terms. So what we're going to look at today is what can we do to generalize this to get higher order. So one way might be if this method is based on taking Taylor expansion, but we stop after two terms, why not just include more terms? So let's take a look at that. So that means that y plus 1 is equal to yn plus delta t f So it starts out the same. And then I have 1/2 delta t squared times something that's based on the second derivative of at time tn. Now, I haven't actually filled this in yet because we can't just say y double prime. I mean, y is what we're trying to compute. But we can figure out what y double prime is using the fact that y prime is equal to f. So if y prime is equal to f of t y, then we'll just take the derivative of that. So y double is equal to, so we got to take the derivative of the entire right-hand side with respect to t, keeping in mind that both arguments depend on t. So there's a multivariable chain rule thing going on here. So we have df dt at ty. And then we move to the second argument. So that's going to be df dy at ty times the derivative of y with respect to t. But that's y prime, which is f. So then we have another factor of f. So this whole expression is what would go in here. So it would be ft of tn yn plus fy tn yn times f tn yn. Okay, so this would be one way to get a method that is at least second order accurate, just by going one term further in the Taylor expansion. Okay. But we actually don't want to do this because this kind of approach requires higher order derivatives of y, meaning derivatives of f. And derivatives of f are not necessarily available or practical. And if f is a simple enough function, then
Might not exist. It
um,
might be zero.
well, being zero is not a big deal, but actually that makes the problem pretty simple. But well, yeah, what if f isn't differentiable? And even if it is differentiable, actually computing a derivative, are you going to use symbolic differentiation if a function has a certain form? But computing derivatives in that manner is not very practical. You can try numerical differentiations. Now you have error involved with that. Also, already at second derivative of y, things got a little more complicated. That complexity would just mushroom if we wanted to go even further to get like third order or fourth order. And it's not necessary to go to all that trouble just to get higher order accuracy. We can use a different approach. So that's the first thing that comes to mind, possibly when trying to get higher order accuracy. But we see that we'd really rather not go down this road, so we're going to back up and try something else. Are there any questions about what happened to this aborted attempt? Okay. So I'm not sure if you need me to,
Yes, I cannot write as fast as you talk, so.
okay. Okay, so we actually are going to make use of Taylor expansion just in a different way, where it's not really part of the method itself. It can be used to help design a method. Um, so, but instead, there's more than one approach to higher accuracy. We're going to talk about one today and a different one next time. Um, use what we call Runge-Kutta methods. So I'm going to state the general framework for Runge-Kutta and then give some examples. So a Runge-Kutta method has this form. It starts out similar to what you see. Y-1 equals yn plus delta t. So right now there's no difference, but until now. So we have a sum j and coefficients, so I'll call bj, and then these vectors I call them kj, and I need to define ups. So so k1 is equal to f evaluated at the argument. So we have Tn plus C1 delta T. And then the second argument, the Y part is Yn plus, and then we have a sum. Okay. This is I, so J. A1I. A1I. All right. And then we have, and then we keep going. So we're all convinced to have any number of these K vectors. A R I I. Right. So each one of these K vectors involves an evaluation of F. And these are called stages of Runge-Kutta method. So there's somewhat a correlation between the number of stages and the order of accuracy of the method. They're not always the same, but generally, if you're going to use more stages, that takes more expense because you have to evaluate F more times. But you want to get higher order accuracy as a result of all that work. Okay. Okay. Now, it's rather cumbersome to describe a Runge-Kutta method by writing out all of this. But we don't really have to. A Runge-Kutta method, you think is being determined by all the coefficients that you have. The B coefficients here, the C coefficients here, and the A's here. So to describe this Runge-Kutta method, RK method, use what's called a filter tableau. Okay. This is named after John Butcher, who is a pioneering researcher in numerical methods for ODEs. I heard that we're having a conference in February for his 90th birthday. But it's in New Zealand. So, right. Visiting speaker that we had a couple weeks ago from Mississippi State, Dr. Luan. he's going to it. So, all right. And then that's how I found out, because the following week is a Siam meeting in Amsterdam, and I'm going to that one. So, all right. Now, so what is the Butcher tableau? So what you do is you fill in, okay, right here you fill in all your C coefficients. And then down below you fill in all the B coefficients. All right, so R is the number of stages in the method. And then you fill in your A's, which form a matrix. Something seems. Okay. CL. I just want to make sure I have this. So. Okay, I'm not sure about the switch. Basically, Martino. So I'm going to look up a different site, Butcher Tableau, just to make sure I have everything correct. Okay. All right. So one R. Okay, so that's the same, and then we have IJ. All right. Well, wait a minute. KJ. Um. Row one. Oh, actually, maybe it is correct after all. Oh. Sorry. Yes, it was correct all along. Okay. So we have CA. So we have a matrix filled in here. Now, it's funny, you get something backwards in your head and it just sticks like that. And we all have a problem with our students. Like, yeah, it gets the wrong idea in the head and you're trying to explain to them and like that wrong idea somehow metastasizes. And yeah, and that happens in every level. Okay. So I guess we're more experienced, a little easier to dislodge it, but okay. Now, these coefficients, the C's, so each CI is a sum J of all the A coefficients in that row. All right. And it makes sense because, oh, sorry, significant something, it's a delta T factor here. Okay. Actually, it's in some versions of Runge-Kutta methods. Actually don't, they include the delta T out here. In front of the F, and therefore not here or here, but different conventions. Anyway, each call to F in one of these stages is evaluating a certain time. So we have a multiple of delta T that we're advancing by. So because we're going to this point in time, all these coefficients add up to this, so that this is evaluated at the same point in time as this. They correspond to one another. So that's why the C's have to satisfy this condition. So, so really, it's the A's and B's that you have to figure out, and the C's will follow from that. Okay. All right. Now, I should mention that the Runge-Kutta method is explicit if the matrix A that has all of these coefficients in it is strictly lower triangular. In other words, Aij is equal to 0 if I is less than or equal to j. Right. And most of the examples I'll show you today have that property. Another way of putting it is each one of these k vectors, it can only depend on prior k vectors. So it can't depend on itself, can't depend on any k's that are defined further down. That would be an implicit method, which means you gotta solve some system of equations to get all the k's. But if we don't have it, if this is the case, it's an explicit method. In other words, you can just plug and chug to get your yn plus 1. So when I introduce examples of Runge-Kutta methods, and I'll write out formulas like this, but I'll also show you with Tableau so you can see how they correspond. Because when I first learned about Runge-Kutta methods way back in 1989, yeah, that was really forever ago. Yeah, so the Tableau thing wasn't covered. Maybe it hadn't been introduced yet. I don't know. Okay, I gotta find out. This on this Wikipedia page that has mentions Tableau. I don't know if it says like when Butcher came up with the idea. Okay. Maybe in the references. Because there's so many references of his dating back to the 60s. Dang. Okay, it doesn't say which one of his many papers introduced that. Yes, it wasn't until much later. Actually, I think when preparing to teach this class for the first time back in 2017, I learned about this. Like, wow, that's overdue. Okay. So, was there any questions about the Tableau itself? Okay, so now we have several Runge-Kutta methods of different orders. mostly explicit, but some implicit too. Okay. So in fact, that's something that we've already seen. Explicit Euler, that technically is a Runge-Kutta method. Okay. So here you have yn equals, or yn plus 1, yn plus delta t k1, where k1 is equal to f at tn yn. So I'm just writing it that way in its Runge-Kutta form so we can see what the stages are. So the tableau for it, okay, it's actually not very interesting. So for one thing, we're evaluating a Tn. In general, kind of have Tn plus something like delta t times a coefficient c, but that's the case that c is 0. Whatever we multiply, we have delta t times a coefficient b times each k. Well, we only have one of those, and b is going to be 1. So we have a 1 here. Okay. Oh, one thing I didn't mention that's worth mentioning now is that the sum of the b coefficients that go in the bottom should be 1. Okay. All right, so really there's
C's are always.
this generally,
Okay.
yeah. Because you're taking a time step of with delta t, you're taking the linear combination of all your k's. So, yeah, and then that's what we'll see in the examples that we have. Okay. So, forgot to mention that last time or earlier. All right. So since we're not adding anything onto this y here, we just don't have anything. Yeah. Okay, I guess we could put a 0 in there, but whatever. I guess apparently the custom is to have a blank space.
What is the, it's always B,
So,
the
on the bottom, yeah. Yeah, the B's sum to 1. Yeah. All right. Implicit Euler. A little weird to describe implicit methods using this format. But in fact, the main part of the method is exactly the same as for explicit Euler. We have y plus 1 equals y plus delta t k1. But k1 is defined differently. So k1 is f of tn plus delta t. So that means we're going to have a c coefficient of 1. And then we have yn plus delta t k1. So notice k1 is defined using itself. So we're going to have, because we have a delta t k1, so there's an implied coefficient of 1 that goes here. And then we have 1 here. So it's an implicit Euler tableau. And because the matrix that we have here is not strictly lower triangular, that's an implicit method. Now, those are both first order. This one's a little more interesting. Explicit midpoint. So for that, we actually have two k values. We have yn plus 1 equals yn plus delta t k2. So k1 is just plain old math. Same k1 as in what's the Euler. Then k2, we take half the time step because we want to evaluate at the midpoint between Tn and Tn plus 1. And then we'll add on Yn plus 1/2 delta t k1. So the idea is here we're taking an explicit Euler time step of size delta t over 2. So this is approximation of y of Tn plus delta t over 2. Using an explicit Euler approximation. And that's why we need this to help us get that approximation. So this whole thing approximates a time derivative at this time, at the half step. And then we use that here. Now the tableau is a little more involved because we have two Ks. So for K1, we're just evaluating at Tn, so we're going to have 0 here. For K2, we evaluated Tn plus 1/2 delta t, so we have a 1/2 here. And then for K2, we multiply K1 by 1/2, so we get a 1/2 here. And then in our formula for yn plus 1, we don't use K1 at all, so we get a 0 here. And then we have delta t times K2, so there's a coefficient of 1 there. Sorry, what?
I didn't get that. Could you
Which?
getting the coefficients?
Okay. What goes here is your multiples of delta t in the time.
Okay.
So we don't have any here, that's the 0.
Okay.
We have 1/2.
That one goes from delta t in.
Yeah, well, for over here, yeah. Yes, so whenever you have a multiple of delta t times a k, that goes over here. So we don't have anything for k1, and then here we just have 1/2 k1. And then the coefficients of your k's in here give me the b coefficients. There is no k1, and then we just have delta t times k2. All right.
Do we always know how many coefficients we're gonna have? Or does it change based on?
Well, I mean, you can have your own kind of methods of any number of stages you want. And then however many stages you make, that's how big your tableau is.
But we can.
Yeah, we're gonna see, well, yeah, the next one we're gonna do is 4 stages. Well, actually, you know what? Okay. Even though it's different order most of my notes, I call this explicit midpoint because we can just plug and chug, like we compute this first and we use this down here, we can work all that out and then use that in here. But there's also, since we have explicit, implicit Euler, we have explicit and implicit midpoint. So the general idea, implicit, I literally just said it. The general idea of the midpoint is you want to evaluate the time derivative at time Tn plus delta t over 2. So, okay. But this one requires only one stage. It's just that one stage is defined implicitly. So we still want to go with half a time step. And we have yn plus 1/2 delta t k1. So notice that this k2 is exactly the same, this k1 is exactly the same as the k2 up here. But now we have a recursive definition. So you'd have to, in order to compute this at all, you have to perform some iteration to solve this for K1. I'm going to use that here. So this has a smaller tableau. And so you're going to have, since you only have one term here, you're going to have a 1 here. And then you have 1/2 delta t, so we get a 1/2 here. And then you have this 1/2 goes here. So your A matrix is just a 1-by-1 matrix, but because you have a non-zero 1-by-1 matrix, it's not strictly lower triangular. So it's implicit. Okay. Now, as I mentioned before, both the Euler methods are first order accurate. These, both midpoint methods, are second order accurate. This comes from a symmetry from using the midpoint. That's why that happens. So we also see, like I said, the number of stages does not always dictate the order of accuracy. And here we have a 2-stage method that's second order accurate, but here's only a 1-stage method that's also second order accurate. Okay. All right, any questions about these two? I have one more explicit-implicit pair that I should mention. Although I only have the explicit one in my notes, so this could be interesting or troublesome, but okay. All right, next method is explicit trapezoidal method. So we have yn plus 1 equals 1n plus 1/2 delta t, k1 plus k2. Now, if you remember trapezoidal rule for integration, what you do is you approximate the area under a curve by a trapezoid. You evaluate the height at left endpoint and right endpoint. Similar idea here, we evaluate the time derivative at the left and right endpoint of our interval in time. So k1 is just the time derivative at the left endpoint, which is tn. And then k2 is an approximation of the time derivative at the right endpoint, which is tn plus delta t. But for that, we need an approximation of a solution at time tn plus delta t. So to get that, what we'll do is we'll take a time step using explicit Euler. So this is an approximation of y of Tn plus delta t by taking a time step using explicit Euler. So even though it's just a first order approximation, that still helps us to get a second order approximation overall. All right. So the tableau, we have two Ks. So for the first one, we're evaluating it just Tn, so it gives 0 here. And then for the other one, we evaluated Tn plus 1 times delta t, so we get a 1 here. And because in the y argument, we have just K1 times just plain old delta t, that gives us a 1 here. And then if we go to our formula over here, K1 and K2 are multiplied by delta t times 1/2. So we have 1/2 here.
Will this be?
Well, it is lower triangular, yeah. Yeah, so there's nothing here.
It's not explicit in this.
Yes. Yeah, that's how we can tell. And it's the second triangular. Now, if I don't have it in my notes, on implicit counterparts. Now the main formula for y plus 1, that's exactly the same. Still wants 1/2 times the time derivatives at Tn and Tn plus 1. And in fact, K1 is going to be exactly the same too. So to start my tableau, 1/2 here, 1/2 here. That part's going to be 0. It's the rest of it that's different. So for K2, we have f of Tn plus delta t, so it's going to be a 1 here. So far, it's looking much like the explicit one, but so for this, I still want an approximation of y at time Tn plus 1. Okay, so that would be yn plus delta t K2. Yeah, let's define it in terms of itself. Okay, so yeah. So that means I am still going to have a 1, but whereas here it's multiplying K1, now it's going to multiply K2, so it goes over here. So the matrix is not strictly lower triangular anymore, thus it's implicit. And both these methods are second order. This subscript should be a superscript. Dang it. Write down this tab below so I can put it in the notes later. Okay. All right. I guess I don't have enough room for the last method. But this is a higher order active than the others, and also really the most popular, widely used Runge-Kutta method. The fourth order, so commonly known as RK4. So yes, it's fourth order accurate. It's also 4 stages. So +1 equal to yn plus delta t. Then we have 1/6 k1 plus 1/3 k2 plus 1/3 k3 plus 1/6 k4. Then here are all k's. Two n plus e 1n plus a1 3 e 1/2 delta a2 4 plus delta b 1 plus delta t 3. Okay. So then tableau will be, all right, so 6, 1/3, 1/6 down below, and then we have 0, half, 1 up here, half, half. Okay. That's everything about fourth order Runge-Kutta.
What was the horizontal coefficients of again?
Oh, these?
No, the K, right?
Yeah, multiples of k in the main step.
Okay, only in the main step.
Yeah.
The bingo. Okay.
Any questions about the? Okay. All right. Now, things when I saw these notes and how it wasn't much here, it wasn't explaining Tableau, but this is not going to take a lot of time. And time to talk about convergence analysis, which I should at least do. I guess it might be an abbreviated presentation, but okay, I'll see what I can do. It's not the notes, but it certainly should be. All right. All the methods that we've seen so far are examples of what we call one-step methods. All right. So I'm going to talk about like the general framework for one-step methods. Don't have this form. Yn plus 1 is equal to yn plus delta t. Some function phi that will take as parameters tn, yn, and also the time step delta t. Now, those functions phi might be very complicated functions, but it is some function that needs these as input. Okay, so I need to define some terms. I kind of did this for working with Ford Euler and showing you its convergence, but I want to show you in general how these things work. Since Euler is such a simple one-step method. Okay. So how you perform convergence analysis. First, you show consistency. So the idea is you have the exact solution is substituted into the numerical method. All right, and then you add on to it delta t tau n or tau. So that is the so tau. I think it's super strong. Tau n is the local truncation error, LTE.
Local truncation error at what?
I don't recall what I said.
At delta t or something.
Well, no, that's local truncation error. It's just I don't recall what I said after that. Okay. Okay. Now, if I take this equation, I rearrange it a bit, and take the limit as delta t goes to 0. I have the limits delta t goes to 0 of y plus 1 minus y n over delta t minus phi n y n 0 because delta t is going to 0 plus okay. Now, that's delta. Doesn't look very delta-like. All right. Now, for consistency, I want the local truncation error to go to 0. Okay, now the limit of this whole thing must be 0 because, okay, what I have here, this is inequality. Oh, sorry. All right. So, but the thing is, what happens once it goes 0? Well, this is becoming, if we think of Tn as being fixed, so I want to emphasize that Tn is fixed. That's y prime of Tn. Okay. And so if the method is consistent, if this whole thing is going to 0, in other words, the local truncation error is going to 0, in order to have this whole thing satisfied, the only way that can happen is I need this must converge to f of Tn y of Tn. So the conclusion is the method is consistent if and only if phi at Tn Yn 0, so the third parameter or time step goes that you set that equal to 0, that must reduce to f at Tn Yn. So this is the condition for consistency. And in fact, if you were to look at any of these Runge-Kutta methods I've shown you, if you just went ahead and threw out and set delta t equal to 0 in your k's, then you would get that. So this is time to go to 0. So the actual definition of consistency is the LT equals 0 is LT equals 0. But to make that happen, you want this. Any questions about that? So it's not hard to check if a method is consistent at all. Now, it doesn't say anything about the order of accuracy. It doesn't tell if it's first order, second order, whatever. Now, you want that. Delta t to the whatever power. That's where you carry out Taylor expansion on your function phi. Now, phi is a function of multiple arguments, so that's a multivariable Taylor expansion. Well, I guess also y of Tn plus 1, we Taylor expand that too. That is a single variable Taylor expansion. So then you're just matching up Taylor expansions.
Okay, so I'm wondering how phi converging to f makes this condition to be satisfied.
Okay.
So
Because y prime equals f.
oh, okay.
Because y of t is the exact first. I should have mentioned that. Okay. All right. That's consistent. Now the other big part of this is stability. Looks like we have for time independent problems with Poisson's equation, but the notion of stability for time dependent problems is very different. Right. So stability, the definition of stability is, so once that method is stable, actually, it's not just one step. Because we're going to learn about multi-step methods on Thursday, and this definition applies to them too. The time-stepping method is stable if you have two solution sequences. So yn and hope everyone yn tilde. That are, so you have different initial data, so y0, y tilde 0, and you use your method to generate computed solutions from both the initial data. Then we have a following. Yn minus y tilde n is bounded by some constant k times the difference in the initial data. Now keep in mind that we're solving this ODE on some interval in time from 0 to capital T. So that's why I have this condition here. So the difference between your computed solution at any time step, however many time steps you take to get to capital T. So across all of those time steps, no matter how, and keep in mind, as delta T goes to 0, the number of time steps you're taking is going to infinity. But across however many time steps you have, the difference between solutions can be bounded in terms of the difference in your initial data. And its constant k must be independent of your time step delta T. Now, now it's pretty difficult to prove this directly for any given method, but we don't have to. Even we're also a simple condition to check, just like for consistency. We're going to assume that your time derivative function f is Lipschitz continuous, meaning that f of t, Lipschitz continuous in the y argument. So y2 minus t y1 is bounded by some Lipschitz constant that I'll call L times the difference in your y values. Notice the t values are the same. So then, a one-step method is stable if phi is, oh yeah, there's a vector value function. If phi is also Lipschitz continuous in y. So in other words, phi of t y2 plus t times phi of t y1 delta t bounded by some Lipschitz constant, which I'll call L phi, times the difference in y values. So the idea is, if you assume f is Lipschitz continuous, then you can find out the Lipschitz constant for phi in terms of the Lipschitz constant for f. So that's all you need to do to ensure stability. For explicit Euler, the Lipschitz constant for phi is the Lipschitz constant for f. So that made that convergence proof a lot easier. So once you have these two things, so again, we have like the lax equivalent sphere. Then you have, if the method is consistent and stable, then it is convergence.
I didn't remember the name of the theorem. I knew the condition, but
Oh, yeah.
I forgot that it's lax.
Yeah. And so in fact, the way you would prove that consistency and stability imply convergence is very, I won't do that here, but it's very similar to how the convergence proof for explicit Euler was carried out, where instead of a Lipschitz constant for f, you have a Lipschitz constant for phi. But the mechanics of it works the same. So, and whatever order of accuracy you have for the local truncation error will be the order of accuracy for the global truncation error. So consistency, as with time independent problems, means that local truncation error goes to zero. Convergence means that the global truncation error goes to zero. So all of that, so between time independent and time dependent problems, the theory is all like isomorphic basically. You just have in terms of how consistency and stability convergence relate to one another and their broad definitions. It's some of the particulars that are different, like how do you define local truncation error for one kind of PDE versus the other? Also, how do you define stability? So So once you have the definitions worked out for both things, then all the theory falls into place. Unfortunately, there isn't time to, what I'd like to do is show how this works for a given one-step method, like show that it's consistent, show that it's stable, also show you how to get the local truncation error. Maybe I can do it on Thursday. But I also have multi-step methods to cover, so we'll see how that goes. But
Is the reverse also true?
I can never remember. Originally, it's a partial converse. Like for instance, I've seen written where, like if a method is consistent, then it's convergent if and only if it's stable.
Yeah, stability denotes consistency, but consistency does not necessarily define stability.
I mean, with convergence.
Yes, convergence defines stability, but not necessarily consistent. It can be consistent, but non-convergent.
Well, let's look it up. Now this one is specific for finite difference.
Possibly, I might have read.
Oh, okay. Actually, this one we're seeing earlier notes for time-independent problems. Okay. If a method is consistent, then it is convergent if and only if it is stable.
Consistency is not.
Because what's interesting is, I know of a finite difference method. It's called the Dufour-Frankel method that is, it's known to be stable regardless of the value of delta t, which is unusual. And I think we'll learn later about about methods being conditionally or unconditionally stable. But the method is not always consistent. So you have to be careful about that. So, but that's an unusual case. Okay. Oh, well, I'm literally out of time. Okay. Well, we didn't have time for homework questions either, but
I
But-
can,
okay. All right. Oh, so you did have some.
I'm sorry,
So you did have homework questions?
a bit, yeah.
Oh, dang. Sorry. Okay.
You have to break.
Okay. Okay.
No, I have homework questions,
Oh,
but I'm also, actually, I'll just tell you next time. See?
okay.